All right, ladies and gentlemen, this is our discussion on molecular structure and acid strength. So if you are watching this for whatever reason, if you weren't in class or we are perhaps not having class today, then just so you know, you should have your note packet out for the acid-base chemistry slides, and this is on page 15. So these are the exact same slides. And this topic, which is the final topic in our acid-base unit, when I say molecular structure, it's really talking about the bonding, the Lewis structure, and how that structure can actually influence acid strength, how well the acid acts as an acid. And it has absolutely everything to do with the bond between the hydrogen in your acid, which is your acidic proton, and then whatever it's bonded to. If it's bonded to A, if it's bonded to O, if it's bonded to a different element, it has everything to do with that bond. The stronger that bond is, the better that bond, the more well-connected that hydrogen is to that other element, means that you're going to have a weaker acid. An acid, by definition, is a proton donor. That means that the acid is capable of getting rid of its hydrogen. Well, think about that. In order for that to happen, that bond has to break. You want a weak bond, because a weak bond will mean that that bond can break more easily. And the more easily that bond breaks, the more easily that hydrogen is donated, which means the better your acid. If you have a very strong bond between hydrogen and whatever it's bonded to, then that means that it's going to take a lot of energy to break that bond, which means that it's not as likely to occur. If it's not as likely to occur, if that bond isn't as likely to break, then your hydrogen won't be donated as easily, and you're going to have a weaker acid. So it has absolutely everything to do with that bond. And there are two factors that we're going to talk about that influence that bond and how well that bond can break. Those two factors are, number one, electronegativity, and number two, atomic radius. I'd like y'all to kind of have a hazard a guess as to which one you think might be more important, which one I might be telling you has more of an effect on acid strength. I bet you can figure out that it's probably not atomic radius, that in fact it might be electronegativity. Electronegativity, as a reminder, as a definition, because this is clearly the more important of the two factors when we're thinking about molecular structure influencing acid strength. As a reminder, that's the ability of an atom to attract electrons to attract shared electrons to itself when it's bonded to something else. So how well that atom can pull in electrons from another source. This is obviously the big one, but we're actually going to talk about atomic radius first. Basically because it's less important, we're going to get it out of the way and then spend our time talking about electronegativity. So how does atomic radius affect acid strength? Well, notice I didn't say, I said how, but the slide says when. When is really a better descriptor. When does atomic radius become the reason that you're looking at acid strength? And really there's only one time. It's when you've got binary acids that are in the same group as one another. Binary, two elements. Binary does not mean two atoms. Binary does not mean two atoms. Water is a binary compound because it contains two elements. However, it contains three atoms. We still call it binary because it only has two elements. So all of our binary acids are going to look like HX. Maybe it's H2X, maybe it's H3X, but they're all going to look like that. There are only going to be two elements total. And the acids, whatever else it's bonded to, the X bit, it's when we're comparing acids that would be within the same group if you take away the hydrogen. And once again, it comes back to this bond. It really is all about the bond between hydrogen and then whatever it's bonded to. In this case, it's that HX bond. The stronger the bond, the harder it is to break, the weaker the acid. Well, how do you make a strong bond? Smaller atomic radius. Remember, this is a Coulombic force of attraction issue. The closer two particles are to one another, the greater their force of attraction. If your hydrogen proton can get very close to that X, because X has got a small atomic radius, then that bond is going to be a lot stronger because those two particles are physically closer to one another. The closer they are, the greater the force of attraction. Well, the greater the force of attraction, that's going to mean more energy required to break that bond. We want to break that bond if we're dealing with an acid because we want that hydrogen to be donated. Harder to break the bond, weaker the acid. Less likely that proton is going to be donated. For this reason, acid strength increases when you're going down a group when you're considering these binary acids. And ladies and gentlemen, this is why our strong acids HCl, HBr, and HI, but we do not put HF in that group. Hydrochloric acid, hydrobromic acid, hydroiodic acid. These are all binary acids. We compare that with HF, also a binary acid. Fluorine, chlorine, bromine, and iodine are all in the same group as one another. However, because fluorine is the smallest of them, the hydrogen can get very, very close to the fluorine because it's small. It's got the fewest electron shells. So the force of attraction between the hydrogen and the fluorine is much greater than between the hydrogen and the iodine because iodine is very large. Because the force of attraction is greater, the bond is stronger. Because the bond is stronger, it is less likely to break. Because the bond is less likely to break, the hydrogen is less likely to be donated, and we are talking about a weaker acid. This does mean that hydrochloric, hydrobromic, hydroiodic, we consider them all strong acids, but they don't technically have the same strength. You can compare relative strengths. And of them, hydroiodic acid is the strongest because the hydrogen is the furthest away from the iodine nucleus. It will feel the least amount of attraction, meaning it will have a weaker bond, but that's a good thing for acids because the weaker the bond, the easier it is to break it, the easier it is for that proton to be donated, the stronger the acid. So that's when we're talking about atomic radius. This is really the only time that atomic radius is our reason for looking at acid strength. The rest of the time that we're talking about acid strength, we are talking about electronegativity. So when does electronegativity impact acid strength? Basically any other possible situation you can think of. What I mean by that, if we have binary acids, but they're in the same period rather than the same group, they're impacted more by electronegativity than by radius. The changes in radius within the same period are not nearly as large as the changes in radius within the same group, because in the same period, you've got the same number of electron shells, you are changing the radius, but it's not by the same substantial degree as when you go down a group. So because the radius isn't changing that much, we really tend to look at electronegativity. Furthermore, if we have ternary acids, as soon as you introduce a third element, that third element, frankly, is going to be oxygen, and then it becomes almost entirely a question of electronegativity. So how does electronegativity affect acid strength? Why is this our main thing that we're thinking of? Once again, it is all about the hydrogen to other element bond that we are talking about. And I don't want to say hydrogen bond because that's an intermolecular force of attraction, but the actual covalent bond between hydrogen and something else. Electronegativity has an effect because of what we call stabilization. If our element or the center of our element is highly electronegative, meaning it's really, really good. We have a very electronegative element. We've got fluorine, maybe we've got nitrogen, we've got things that are in the upper right-hand corner of the periodic table. Then, by definition, because it's highly electronegative, they are very good at attracting electrons to themselves, which means if you were to break the bond between hydrogen and the rest of the acid, you would now have a positive hydrogen and a negative rest of the acid. Stability means that the more electronegative the rest of the acid, the more stable that negative charge is. Because electronegative means it kind of wanted to pull the electron to itself anyway. So it's fairly stable with that negative charge because it wanted that electron. It was pulling it away anyway. Also, the more electronegative, basically it's sort of pulling the electron, the shared electrons in the bond towards it, which can be a way of essentially weakening that bond. We say it's destabilizing the bond. It's making the bond less stable and more likely to break. If the electrons aren't being shared equally, if one side is really sort of sucking the electrons towards it because it's highly electronegative, we say that bond is getting destabilized, which is a good thing for acids, because the more destabilized the bond, the easier it is to sever the bond and be left with your proton, your H+, and then the rest of your acid, which will be A-, which is now your conjugate base. So we're looking for basically a way to increase the electronegativity of the not hydrogen part of the acid, because that will actually make it easier for that hydrogen to simply pop off, because we say it destabilizes the bond. It doesn't make the electrons in the bond being shared equally. The electrons are being pulled away from the hydrogen, making it easier for the hydrogen to become H+. Essentially, they're almost like pre-losing the you're turning your hydrogen into an H+ sort of sooner by pulling the electrons away. So, saying this here in words on the slide, what I've basically been explaining, we have a highly electronegative center of our atom, either through an element or multiple elements. Your hydrogen is already mostly H+, your A is already mostly A-. Not much energy is needed to break that bond. It will be easier to donate the H+. Ways to increase the electronegativity in the anion and the acid. So how do you do this? How do you have a more electronegative center of your atom? There's a number of ways. Number one, you can have a more electronegative central atom. So you can change what the central atom is. This would be like NO3 versus H2SO4. You've got different central atoms in those cases. You've got nitrogen versus sulfur. The more electronegative your central atom, the greater the pull of electrons away from the hydrogen, the easier it is for that hydrogen to simply pop off, and the stronger your acid. More than that, though, you can add extra highly electronegative atoms, like oxygen. Oxyacids are what we call basically the acids that you can think of that we've seen in class, like sulfuric acid, H2SO4, like nitric acid, HNO3, like chloric acid and perchloric acid, HClO4, HClO3, which are acids where we have a central atom that's bonded to oxygens, and one of those oxygens is bonded to a hydrogen. So these oxyacids are the non-binary acids. We don't really consider water totally an oxyacid. It would more be along the lines of HClO3 and HClO4. Key, absolutely critical point about the oxyacids, however, this is crucial. In our oxyacids, the hydrogen is not bonded to the central atom. The hydrogen is bonded to an O. So this breaks a little bit with what we're used to seeing with our Lewis structures, where the very first element listed is the central atom. This is not the case with acids. It can't be, because the first atom listed in acid formula is a hydrogen, but hydrogen can only ever make one bond. So it can't be at the center. In fact, the one that's at the center is the one that usually comes second. Now, we're also kind of used to this concept of order, of saying that the order that the atoms might be listed in might be the order that we're going to draw them in. Like HClO4, you might want to say the H is bonded to the Cl, and then there are 4 oxygens coming off of the Cl. That is not the case. In oxyacids, the hydrogen is bonded to an oxygen. Pick an oxygen. And then the oxygens are all bonded to the other thing. So we're going to look at the structure of some oxyacids on the next slide, where you'll see this. Your hydrogen is not bonded to the central atom. It's actually bonded on the outside. For that reason, this can create an electronegative pull away from your hydrogen, and it will make the H+ more stable. It'll destabilize the bond, but make your H+ more stable once the bond breaks. That makes it easier to break the bond, easier to donate the proton. So these are some oxyacids. These are our strong oxyacids. It's HClO3, HClO4, HNO3, H2SO4. In all of these cases, what's critical for you to look at, perchloric acid, this is HClO4, but you see that's where your hydrogen is. Your hydrogen is not bonded to the chlorine. So this is the bond that has to break, so that the ion that we get is the perchlorate ion and then H+. Nitric acid, this is HNO3. Again, hydrogen not bonded to the central atom. The hydrogen is bonded to an oxygen, which is then bonded to the nitrogen, and that's the bond that we're severing. Sulfuric acid, H2SO4, we do have two protonizable protons here. Neither of them are bonded to the sulfur. They are both bonded to oxygens. And chloric acid, this is HClO3. Our hydrogen is not bonded to the central atom. Instead, it's bonded to an oxygen. So with that in mind, we're going to go through a couple of examples of comparing the relative strengths of these acids based on what we know. So this first one, HF versus H2O versus NH3. Now these are three compounds, and basically we're trying to compare which one is most acidic, which one is least acidic, and why. If we look at the periodic table, we're not focusing on the hydrogen, focusing on the other parts. So we're thinking about F, O, and N, and we see that those are in the same period. Think about what I said influenced acid strength. We've got atomic radius and we have electronegativity. When does which influence it? Atomic radius influence acid strength when we're dealing with binary acids. Are these binary? Yes, they are, but we're not done, because atomic radius is about binary acids that are in the same group. F, O, and N are not in the same group. They're in the same period. So this becomes a question of electronegativity. The more highly electronegative the non-hydrogen part, the easier it will be for the hydrogen to other atom bond to break and donate the proton, the stronger the acid will be. Fluorine is the most electronegative of these, obviously, we know that, and nitrogen is the least electronegative of these three, which means that HF is going to be the strongest acid of this bunch, which should make sense to you if you were looking at this list, because we have hydrofluoric acid, which we know is a weak acid. Then we're comparing that to water, which we generally accept as being neutral. And then we're comparing that to ammonia, which hopefully by now you're starting to realize is a weak base. This explains why when you're moving across the period, you're going to get a more highly acidic compound as your central atom gets more electronegative, even if you don't have oxygens involved, even if you don't have an oxy acid. The next two, H3PO4 versus H2SO4. You are now no longer allowed to simply say, well, H2SO4 is a strong acid because I memorized it, Mrs. Julie, and that means it's stronger. Yes, thank you. Why? Why is H2SO4 stronger than H3PO4 in terms of molecular structure? We've got atomic radius, and we have electronegativity. This is not a binary, these are not binary acids, these are ternary acids, so our reasoning is going to once again be electronegativity. Now, they have the same number of oxygens in each one, right? So that's something that they have in common. They have different numbers of hydrogens, but that won't explain why the hydrogen will be more easily donated in one than the other. So we have to look at what the central atom is, the phosphorus versus the sulfur. And if we look on the periodic table, sulfur is more electronegative than phosphorus based on its position. This means that in H2SO4 you're creating a very strong electronegative pull of electrons away from the hydrogens, which will turn your hydrogens more into H+, making it easier for the bond to break, making it a stronger acid. HBrO3 versus HBrO4. Again, these are ternary acids. Automatically, that comes down to a question of electronegativity. Again and again and again, like I said, this is the most important thing influencing acid strength. What do these acids have in common? I look at their structures, and simply from their formulas you can see, well, okay, each of them only have one protonizable proton, they're starting with the H, and each of them have bromine as the central atom. So what's the difference in their structures? 3 oxygens versus 4 oxygens. Why is that key? This is a question of electronegativity. Oxygen is a very electronegative element. It's the second most electronegative element on the periodic table apart from fluorine. So what we've done in HBrO4, by adding an additional highly electronegative atom, you have made the center of the atom, the center of the molecule, excuse me, more electronegative. You added basically another player to your tug of war between your hydrogen and the rest of the molecule. You just added a very strong player, someone who is capable of pulling the rope towards them very, very much. This will make it harder, much harder for the hydrogen to sort of win that tug of war, and it'll make it easier for the hydrogen to lose the tug of war, which is what we want. We want the hydrogen to be donated. We want the hydrogen to break the bond between it and the rest of the molecule. So adding in that additional oxygen makes that acid stronger. You've essentially given strength to the side that's pulling electrons away from the hydrogen, making it easier to break that bond between hydrogen and the rest of the acid. And then the last example, H2SE versus H2S, where it's always about two possibilities. Electronegativity and atomic radius. Now we do have binary acids in this case, so we kind of have to go back and think, is this about electronegativity, yes or no? So we're comparing what it's bonded to. Sulfur versus selenium. If you look at the periodic table, sulfur and selenium are in the same group. This is a question of atomic radius, because now there is a significant difference in atomic radius between the sulfur and the selenium. If we check on our periodic table, we see that selenium has got 4 electron shells versus sulfur only having 3. And if we think about what that means, selenium is larger. Coulombic forces of attraction say that the further apart two things are, the less the attraction between them. That is a good thing for acids. We do not want the hydrogen to be very attracted to the rest of the acid, because if it is, then it will be harder to get it to go away, to get it to be donated. So if we're comparing this, the H2SE is going to be the stronger acid, because the H2SE bond will be weaker. It's weaker because selenium is larger. So the hydrogen is physically further away from the selenium, meaning it will be easier to sever that connection and have that hydrogen be donated to something else. So that's the discussion on molecular structure and how it influences acid strength. At this point, hopefully you can complete the homework on that.